Okay, hi everybody. Idil, can you just confirm that you could hear me, please? Yeah. Okay. So my name is Corey, and I'm a software developer at Genetec. I've been working at Genetec for about almost 2 years now. I went to Concordia University and I did the co-op program, and I actually found Genetec because I did my internships there during my studies. So today I'm going to be giving the workshop on asynchronous and multi-threaded programming. And with me is my colleague Idia. He'll be around to answer any questions throughout this workshop. If you write them in the chat, he'll be the one answering. So Idia, you could introduce yourself. Oh, we can't hear you. Okay, well,
Hi.
Yep, now we hear you. Good.
Okay, I don't know why. Yeah, I'm Ider Kasha. I'm software developer at Genetec since 2018. And I graduated from Polytechnic of Montreal in 2016. I'm here to assist Corey today in the background to try to answer as many as possible questions. So do not hesitate to ask questions in the chat, and I will be here to answer.
All right, so let's begin. I'm going to share my screen. Okay. Sorry, 1 second. Okay, so as I said before, this workshop is on asynchronous and multi-threaded programming. Just a disclaimer, you don't need to know what asynchronous and multi-threaded programming is. We're going to go over all of it from scratch. Okay. So the agenda for today is first we're going to explain, well, what is multi-threaded and asynchronous programming. Then I'm going to talk about the advantages of using C# with this type of programming. And then finally, we're going to discuss the common problems and how to solve them. Well, a few of the common problems. So what is multi-threading and asynchronous programming? First, there's a few definitions that we need to go over because I'm going to be using these terms a lot throughout the presentation. Firstly, there's threads. Put simply, threads are a way for a program to split itself into 2 or more simultaneously running tasks. Threads are a small sequence of code that shares resources and shares like the executable code. Next, we have synchronous, and synchronous is when you run operations on the main thread and the main thread locks until the operation completes. Next, we have asynchronous, where we run operations on a different thread and the main thread is not locked while operations run. And then there's 2 more definitions I want to go over. Single threading, which is when you process one command at a time, and multi-threading, when you process multiple commands at a time. So I know that probably these definitions don't really make that much sense right away. So let's put this all into an analogy to make it more concrete. So there's like a very famous analogy to explain this type of programming, and it's the breakfast analogy. So the goal is to make toast and eggs. If we would do this synchronously, we need to wait for each operation to complete before we start the next. So let's say at time 0, I start my eggs. 3 minutes later, I start my toast. And 3 minutes later, after that, everything is complete. I can put my breakfast together, and the total time it took was 6 minutes. Now, if I would do this asynchronously, single-threaded, I would first, at time 0, start my eggs. And then once that started, I wouldn't waste my time. I would start my toast. Then 3 minutes later, my eggs would finish. And then I would still have to wait another minute for my toast to finish, and then at minute 4, everything is done, and I could put my sandwich together, and the total time it took was 4 minutes. Now, if I would do this asynchronously multi-threaded, I would have to deal with multiple workers. So I have one worker who would be responsible for making the eggs, and the other one for making the toast. They would both start at minute 0, and then 3 minutes later, the eggs would be done and the toast would be done, and we could put everything together, and we would have our sandwich in 3 minutes. Now, the difficulty in this scenario, though, is the sharing of resources. Imagine we needed the oven to make the eggs and the toast, but at different temperatures. We would have to manage the sharing of the oven to figure out who gets the oven when. So it makes it a little bit more complicated. I'm going to talk about multi-threading versus asynchrony. So threading is about workers and asynchrony is about tasks. So in our asynchronous single-threaded example, we have one worker who is responsible for completing multiple tasks. We are more concerned about the tasks that need to be completed than the worker who is doing it. In our asynchronous multi-threaded example, we have 2 workers, each responsible for their own tasks. In this scenario, we are more concerned about who will be doing which task and scheduling our workers so that everything gets done. Why should we use asynchronous programming? Well, to improve our user experience. That's the main reason. In many cases, the current thread is the UI thread, and as such, synchronous programming causes the UI to freeze quite a bit. So I'm going to show you an example to make this clearer. In this example, I'm loading a file synchronously. So here I have my UI, I have a text box where I'm able to write, and now when I click on load file, my entire UI freezes. I cannot write in my text box, I can't click on any buttons or do anything, and then all of a sudden my file is loaded and everything unfreezes. Well, that's not really a good user experience. There must be a better way to do it, and in fact there is. If we would code the exact same thing, but asynchronously, our user interface doesn't freeze. So we see our text that is loading. We're able to continue writing in our text box. Everything is just a much better user experience. So why don't we always use this? Well, there's certain places where we should be using asynchronous patterns, and that's for input-output operations such as reading or writing to the disk, memory, web APIs, and databases. But there are pros and cons to using this type of programming. The pros are that as we saw, there's clearly a better user experience. Typically the code runs quicker, but there are many cons. The code is more complex, and you could have negative side effects if not used properly. These side effects could be a deadlock, infinite async await, memory leak, ThreadPool starvation, and so on and so forth. Now, these cons are just like, you have to be aware of it because it could be avoided if you know how to code correctly. And I'm going to go over how to solve these as well. So why should we use C# when coding? Why should we use C# when coding? So we're going to go over a few definitions again, the first one being callbacks. So in computer programming, a callback, also known as a call after function, is any executable code that is passed as an argument to other code. That other code is expected to call back the argument at a given time. So a callback doesn't need to know what it's doing, it just needs a signature. And there are multiple ways of doing callbacks. We have delegates, actions, functions, and predicates. I'm going to go over each one in more detail. So a delegate, this is what it looks like in the code. So to declare a delegate, you have the keyword delegate and you pass a parameter. And so, and you have your return type. All delegates, all acceptable delegates must match the signature of the one declared over here. So for example, if we would look at this over here, we have our process that takes an array of delegates that we call callbacks. And everything that we pass, all of our callbacks have to match the signature of our process result delegate. So if we look at our main, we call the method process, and we pass two methods with it, log result and validate result. And if we look at log result, the return type is void, and it takes one integer as a parameter. And that is the same with validate result. So now let's say we would run this code. What do you think that the output would be? So we'll go through it together. First, we call process. So we write to the console, process started. Then we call our callbacks. First, we have log result. So well, first we query our data, and that just gets a random number between 1 and 10. Let's say for this purpose, our result is 6. So we call log result, which writes to the console, result 6. And then it calls our second callback, which is validate result. And so result is valid, true, because it is greater than 5. And then we have our continue with, our task is completed. So it writes task successfully completed. Yeah. So now we have actions. The important thing to note with an action is that they must return void. So the types in these triangular brackets are input types. So N1 and N2 will both be integers, and it returns void. In this case, we have a method that takes an action, and it performs the action with the numbers 1 and 2. So here we call do action with display numbers action. We will be writing to the console N1, 1, N2, 2. Now we have funcs, and a func takes input parameters. It has inputs and an output. So these two are the input type, and this is the output type. The last one is always the output type. So my add func takes N1 and N2 and returns N1 plus N2. And the subtraction func takes N1 and N2 and returns N1 minus N2. And if we run func and print result, what this does is it will write to the console what is returned from our function, which is either the add or subtract. So if we run the add, it will write the result of 1 plus 2, which is 3. And if we do the subtraction, it will write 1 minus 2 to the console, well, the result of that, which would be -1. So next, the last one is a predicate. A predicate represents the method that defines a set of criteria and determines whether the specified object meets those criteria. So here we have our predicate. It takes, this type is the input type, and a predicate always returns a Boolean, either true or false. And in this case, the predicate is checking that our input is greater than 5. If we go through this program, we have a random list of numbers that we're populating. So this list contains 20 numbers, 20 random numbers. And then here, we're doing numbers.findAll. FindAll is a method that takes a predicate. So we're finding all the numbers that meet this predicate, which means that we're finding all numbers that are greater than 5, and then we are writing them to the console. Next, I want to go over some events. Events enable a class or object to notify other classes or objects when something of interest occurs. The class that sends the event is called the publisher, and the class that receives the event is called the subscribers. So here we have our event, which is based on a delegate. This would be what our publisher class looks like. And then if we have our subscriber, we have our event handler. Now, it's important that if we want our event handler to be subscribed to the event, in C# we have this syntax where we do event plus equals event handler. And then when the event is invoked, our event handler is notified. And a really important thing is that when you no longer want to receive events, you have to unsubscribe. So to unsubscribe in C#, you do event minus equals event handler. Now let's take a look at the code to see exactly what this would look like. So here is our publisher class. We have an alarm event enumeration that contains the different types of alarm events that you could have, like alarm triggered or alarm acknowledged. Over here, we have alarm args, which is the arguments that we pass with our event, and that's just the event type, and here is our constructor. And then finally, we have our publisher class. So over here, we have a delegate, and the return type is void, and it has two parameters, an object and an alarm args. And then our event that is based on the delegate. The type of our event is alarm event delegate. And then here's how we raise the alarm event. Now, if we look at our subscriber class, what's important is that we register to the event. So let's just go through this quickly. We have our publisher. Here's our constructor. We have our publisher, and we're registering the process alarm received. If we look at our handler, the process alarm received over here, we see that it matches the signature of our delegate, and so it's accepted. The return type is void, and the parameters are object and alarm args. And so it matches, the signature matches, and it's correct delegate. And a correct handler, sorry. And over here, the way we subscribe to it, as I said, is we do our publisher dot alarm event received, our event, and we do plus equals a handler. That's how we subscribe. And now let's say we're done, we no longer need the event. We're going to dispose our subscriber. And in our dispose, we must unregister our handler. So here we do it by minus equals. If not, you could have many problems like memory leaks. Okay, so next I want to talk about .NET threads. There's a .NET thread. You could create it yourself, or you could use the .NET ThreadPool. This, I'm going to show you how you create threads on your own. So here, you would create your thread by just making a new thread, but you assign it. You can do thread is equal to new thread, and then you assign you set a bunch of properties, and then you need to start your thread. You let it execute, and it's really important that you wait for your thread to finish before completing your program, because otherwise you might complete your program without your thread being done. Now, this doesn't look like a lot of code, but I'm going to explain why using the .NET ThreadPool is actually better. So here, the .NET ThreadPool is managed by the system. It allows the user to reuse threads. It reduces the cost of creating threads. So how would you use this? You could do threadpool.queueUserWorkItem and pass a callback, or you could use the parallel task library where you do task.factory.startNew or task.run. So this is what the code would look like if you're using the .NET ThreadPool. As I said, you could either do task.run, or you could do threadpool.queueUserWorkItem. Similarly to before, you have to then wait for your task to complete. Now, if we would compare the code, this was the code used if there's no ThreadPool, and this is with a ThreadPool. I know that it doesn't look like you have a lot less code when using the .NET ThreadPool, but imagine you had to create 20 or 30 threads, and you had to write all this code each time to create the thread. Well, you see that it actually is significantly less code. Another advantage of using the .NET ThreadPool is that .NET deals with the orchestration and the maintenance of your threads for you. So that is like a huge advantage, and we're going to talk about that a bit more later. Next, I want to discuss async await. All asynchronous methods have the keyword async. The block of code calling an async method contains the word async. And async await is a state machine. So under the hood, it is implementing the iasync state machine. So the compiler transforms the async method and generates a class that implements an iasync state machine. This class keeps the state of each method throughout the whole lifetime of the asynchronous operation. Local variables are encapsulated, and the code is divided into sections that will be executed during the transition between states. I know that this doesn't mean much, so let's look at an example to really understand how this works. So over here, we have a lot of console write lines. I want to give you guys a minute to put these outputs in order, and then we'll go over it together. So take a minute and yeah. Okay, I know that it hasn't been a minute, but we have a lot to get through, so I'm gonna go over the answer now. So we start with our main and we write prepare toast async. And so we go and we write started toast. Now we get to this task.delay. I'm sure many of you think that we just wait here for 2 seconds, but actually we don't. The async state machine knows to go back here in 2 seconds, but it won't waste its time waiting here. It's going to continue. So it goes to task 2, cook eggs async. And it writes to the console, started cooking eggs. Now we get to another task.delay. And again, the async state machine will know to come back here in 1 second. And so it will continue and it will write to the console, do stuff. Now we get to a thread sleep of 5 milliseconds. We wait. Then we write to the console, do other stuff. Now here is the important part. We get to a task.waitAll. Now this means that we have to wait for our tasks to complete before we move on and finish like our program. Now imagine if we didn't have this, we would put our eggs on our toast without actually the eggs and toast being completed. So that's why this is important. So now our async state machine knows that this the 1 second delay will be done first. It goes here and it writes to the console, finish cooking eggs. And then it will go to our other await and it will write to the console, finish toast. Now all of our tasks are completed. We can move on to our next step, which is put eggs on toast. And so we write to the console, breakfast ready. So as you can see, it's extremely powerful, this async state machine. So when would you use async await? You would use it in input-output operations. So when your code is waiting for an operation having to do with a file, database, call to a web service, etc. Now we would use it for CPU operations. So when your code performs complex calculations that consume a lot of CPU time. And there's a couple things that you shouldn't do with async await. You should avoid async void. It's important to return a task whenever you can because the tasks gives you all the information about the execution. For example, it will tell you if there is an error during execution. If you return void and there is an error, your task will fail silently. So yeah, async void is only permitted in the case where the method is an event handler, the method is a callback. Otherwise, return a task. Next, async await is not always required. In this case, over here, it's better off that we return a task rather than async await because we're not doing anything over here. We're just returning the await. I know that this looks like we're just adding 2 extra keywords, like what's the big deal, but really it uses up a lot of resources unnecessarily. So only use the async await when you actually need it. And you should avoid long operations and async methods. So over here in this method, get photo stream async, we get a response and then we're reading a stream, but we're not doing this asynchronously. This takes a long time and we're doing that inside an async method, and that's not good practice. What we should be doing is that since this is async, everything should be async, and when we're reading to the file, we should read it asynchronously. So you should do async all the way. What this means is that you shouldn't mix synchronous and asynchronous code because you can easily run into problems like deadlocks. Next, I would like to talk about the dispatcher. So here, the dispatcher manages a queue of tasks to be executed on a thread. There can only be 1 dispatcher per thread. And these are different ways that you could invoke your dispatcher. The reason why I'd like to talk to you about the dispatcher is because it's important in like WPF applications where when you want to update the UI, you have to do that through the dispatcher thread. So by default, the WPF application starts with a dispatcher, and a dispatcher object can only be accessed by the thread that created it. Next, I want to talk about parallel for each loops. So similar to a parallel for each is similar to a for loop, except that the collection is partitioned and the work is spread over several threads. Threads are spread over several processors or cores, and the more the processors, the better the performance. Well, almost. That's actually, there are traps that we have to avoid. And these traps include over parallelism, calls to methods that are not thread safe. We should never assume that a parallel for each is always faster than a simple for each loop. And we have to consider the cost of thread creation and of thread synchronization. Just like a quick side note, actually, yesterday I was looking into a bug that was opened by one of our teams at Genetec, and the cause of the bug was actually that they were using a parallel for each, and there were some traps that they were not avoiding, and that ended up causing a bug that took a couple hours for everybody to solve to figure out what the problem was. So really, when you're using parallel for each loops, we have to know what we're doing. So here's an example of what a parallel for each loop looks like in the code. Over here, we have our parallel for each, and our source is this list of website URIs. And now over here, we're setting our parallel options, and it's really important to set the max degree of parallelism because you don't want to use up all of your computer's resources. And then here, we're downloading and storing. So here, what we do is we're passing our list of website URIs, well, our string URI, and we're adding it to our website data. And over here, we're using a concurrent bag because a concurrent bag is thread safe. A concurrent bag is similar to a list, just it's thread safe. And so this is how you would use a parallel for each loop. Now I'm going to show some common problems that occur when with asynchronous and multi-threaded programming. So the first one I'd like to go over is a deadlock. A deadlock is a condition where a program cannot access a resource it needs to continue. When an active application hits a deadlock, it may hang or become unresponsive. So what does this mean? Well, over here we have two processes, process 1 and process 2, and two resources, resource 1 and resource 2. Process 1 begins and it needs resource 1, and so resource 1 is assigned to process 1. Process 2 then begins and it needs resource 2, and so resource 2 is assigned to process 2. Now, in order for process 1 to complete, it needs resource 2, and so it waits for resource 2 to become available. Process 2 needs resource 1 to complete, and so it waits for resource 1 to become available. And now we are in a deadlock. Let's look at an example in the code. So over here, I have two bank accounts, account A and account B. I'm just going to be transferring money between the two accounts. So here I transferred $200 from account A to account B. And then I'm going to transfer money from account B to account A. Now, what happens if while I'm in the process of transferring from account A to account B, I transfer from account B to account A? Now we see that my loading symbol is forever there, and it seems like we are in a deadlock. Okay. So in a real world scenario, the cause of a problem is not so obvious. So how do we go about figuring it out? Like in this bank account example, we all know that it's clearly a deadlock. When you have hundreds of thousands of lines of code, it's not so simple to know that it's a deadlock. So what I would do is first I would generate a dump file, and then I would analyze the dump file. For those of you that don't know, a dump file is a snapshot of all executing processes and modules that were loaded at the point in time that the dump was taken. So how do we generate a dump file? Either through the task manager, where you look for your process, you right click on it, and you click create dump file. You could also use a program called procdump, where you go through the terminal, the command prompt, and you generate your dump. And then we go about analyzing it. I personally like using the tool debug diag as just like the first analysis, because if there's like a simple problem, debug diag typically is able to bring that to your attention. So it's a good like first analysis. So this is what the interface looks like. You just upload your dump file. I chose to do a crash tag analysis, and then you click on start analysis. And then you get a summary or analysis report. And when you look at your analysis report, it will tell you some errors, warning, information. And now when I look at it, I see something fishy over here, that I have 2 threads that are waiting to enter a .NET lock. Well, that's very suspicious, because my symptoms seem to look like a deadlock. And now if I click on the call stack, I see that there is a method in my application that is in that call stack. So I'm going to look now at my other thread that is stuck at that .NET lock to see if the same method is in that call stack. If it is, it's kind of an indicator that I should maybe open the code and look to see what's going on at that point. And sure enough, it is in that call stack as well. So the next step would be that I am going to open up the code and take a look to see exactly what's going on at that point in time. So when I open up my code, I saw in the call stack that this was the method that was causing the problem. And I see that what the issue is. Each account has its own lock. Now, why is this a problem? Let's take a look. Here, my 2 processes are withdraw from account A and withdraw from account B. And my 2 resources are bank account A and bank account B. Process A starts withdraw from account A, and it locks account A. Now, while I'm stuck in this while loop, account B, a withdraw from account B starts, and account B is locked. Then we continue executing, and account A needs account B to continue. However, account B is locked by the process withdraw from account B. And then withdraw from account B cannot continue because account A is locked from the process withdraw from account A. So here we are in a deadlock. So how do we fix this? Well, we would use a shared lock. The moral of the story is lock with caution, or else you might end up deadlocking. And also, once you figure out what type of problem it is and where the problem is in the code, the solution is typically easy. The hard part is analyzing your files to really figure out where you should be looking in the code to solve the issue. All right. Now, the next common problem that I want to talk about is infinite async await. Infinite async await is when you call an async method and you never get a response. So let's say you have a client and they say they're running a software and no data is ever coming back. This could be an infinite async await issue, but how would you narrow down where the problem is when the software could be huge? Let's take a look at an example of an infinite async await. So here I'm loading contacts from a file, and that's all good. Now if I try to load my contacts from a database, I'm just never getting the results. It's not crashing. My UI is not freezing, but I'm not getting the results. So what I'm going to do is that I'm going to create a dump file. And then I'm going to wait around a minute, and I'm going to create a second dump file. The reason for this is because I want to be able to compare my memory snapshot at 2 different periods of time to see if I'm still awaiting the same tasks at those 2 periods of time. So now I have my 2 dump files created, and I am going to open them in Visual Studio. Visual Studio is actually very powerful for debugging dump files. I always recommend using the latest version of Visual Studio because when debugging dump files, because they just always keep on building on their debug methods, and yeah, it's very powerful. So over here, I opened up my file in Visual Studio and I'm starting the debugging. Just in this video, I skipped over it because it took a while to load, and I think now it's loaded. And I'm going to go and look at all of my tasks. And so here I see that I have 4 tasks that are awaiting, and I see the location and I see exactly which tasks they are. And I see that there's a bunch that are actually within my my workshop, well, my code. And this is really suspicious, but I can't be certain that this is actually the source of my problem, because maybe it just so happened that at the time that I took the snapshot, we were awaiting those tasks. So that's why I took the snapshot a minute later, so I could see if a minute later I am still awaiting the same tasks. And what I'm doing now is the exact same thing as what I did with the previous dump file. I'm gonna debug it, and I'm going to look to see which tasks are loaded at that point in time. So here I open up the tasks, and I see that the same tasks are still being awaited. So this gives me an indication of where I should be looking in the code to see what the problem is. Okay. So now we look at the code. As I said before, we have the same tasks awaiting 1 minute apart. And so I'm going to look at, I'm going to look for the university workshop on load contacts from database. Over here, I see that it awaits the get all contacts. So I'm going to look there. And I see over here, I have the table manager. This is a third-party library for managing my database. And I'm getting my, oh, sorry, this is never getting the response over here in the table manager .get table data for the contacts. So how do I fix that? Well, I would use cancellation tokens. The cancellation token enables cooperative cancellation between threads, ThreadPool work items, or task objects. Now, the thing with the cancellation tokens is that I'm not actually solving the problem where I'm getting a response back from my third-party library. Like, I can't fix that. The problem isn't in my code, it's in another library of code that I'm using. But what I can do is I can make my users' experience better by either canceling the task if I'm not getting a response, or like I could just manage it, and I manage it with cancellation tokens. So what do I do? In my if I go back and you see over here, sorry, we have a clear button, and we have our load contacts from database. So what I'm going to change in my code is that over here in my clear button, when I'm going to introduce my cancellation token, and when I click on clear, what I'm going to do is that I'm going to cancel my cancellation token, which is going to cancel my tasks. And on my on load contacts from database, what I will be doing is first I'll be checking to see if I have a cancellation requested. If my token has already been canceled, I'm going to create a new one, and I get my token and I'm going to pass it to my get all contacts method. And then over here, if I see that my request has been canceled, I'm just going to change my status to request canceled, and it will, and my task will then be canceled. So over here, I have get all contacts, and I'm awaiting my get table data. And what I'm going to change this to is get all contacts and pass a cancellation token. Now, all well-designed third-party libraries will have a option to pass a cancellation token to any async method. So that's also an indicator of if a third-party library is well designed, because you should be able to pass a cancellation token. And so over here, what I do is that I check to see, when I'm getting all of my contacts, I check to see if my task has been canceled. If it is canceled, then I'll return null. And if it's not canceled, then I will return a deserialized list of my response, which in this case is a list of contacts. All right, so that's all the time that I have for you guys today. This workshop is a little bit short, but I hope that you enjoyed it, and I hope that Idil was able to answer all the questions. And if anybody is interested in joining the Genetec team, I highly recommend reaching out to Olivier Julien, who is our university relations coordinator. There's always a ton of internship opportunities available at Genetec. So hopefully I'll be seeing you guys around Genetec in the future. Thank you.